Hello everyone, this is Sumerian, and this is part 3 of the tutorials on using your satellite receiver to move large numbers between toy boxes. Now before we start, this tutorial is actually going to be mostly on how to subtract numbers from this system as well. The only thing I've added to this toy box is I've added these color changing blocks right here, and all they're doing is they're showing the state of the stations on the satellite receiver. If the station turns on, the associated color will turn green, and if it's off like they are right now, they'll show red. And this block is the lowest significant bit, so it is the one that represents 1, 2, 4, 8, 16, 32, 64. Now, a few things first. I believe in my first video, you saw me create an empty toy box using the toy box door. I only did that because it's a tutorial and I didn't really care if I lost the toy box that's through that door. But don't ever do that in real life. Make all your toy boxes separately and then import them once you're done everything. You'll go into the box and you will actually change it. Instead of new, you'll import toy boxes, and that way there's a little glitch where occasionally these doors lose their link. And if you've made the new toy box from within this toy box, there is absolutely no way to get it back. While if you've made all your toy boxes separately, at least you can relink and change a few things that you had already updated, and you're back in business. But if you do it by creating a new toy box from within your current toy box, if that link gets lost, you're SOL. So don't do that. The second thing I want to mention is the way the system is right now. There is a problem with this system in the fact that if you hit 127, which is the maximum number that this 7-bit system can reach, if you hit 127, what's going to happen is every single station will be on. All of them will be on. So if you add another number, what's going to happen is the system is going to turn all of these off. And if we had an 8th bit, it would turn that on, and the 8th bit would represent the number 128. But we don't have an 8th bit, so all that's going to happen is every single one of these stations will turn off, so you will be back at the count of 0. So either put in some sort of system to control that, or just ensure that don't cut it too close, is what I'm saying. If your maximum score is going to be 125, but a really good player could get higher than that, perhaps you want to go 8-bit, because a good player could actually end up with a score of 2 or 3 at the end of the event, which is not good. Alright, so actually first off, I'm going to show you how to put in a little control. It's going to be a simple one, and all I'm going to do, is I'm going to put up another logic gate, and if you remember, we're using this button right here to increase the counter and to input into the lowest significant bit. So I'm going to actually remove those links. What I'm going to say with this button is I'm going to say, if you're pressed, input to this new logic gate of ours. And this new logic gate is going to output an increment +1 to this counter, and it's going to output the input into our least significant bit, so that every time we push the button, it'll add or increase the number by 1. And then what I'm going to do is I'm actually going to use this counter to control something now. And I'm going to change this counter to the number 127, because that's the number we want to stop at. If you reach there, don't go any further. So we're going to set it to 127. And we're going to say, if the target is reached, close this logic gate. So now if you push the button, nothing will happen anymore. You've reached 127 and you're done. So that is one way to put a safeguard into your system so you don't accidentally reset the whole system. So now what we're going to do is I'm going to show you how we're going to subtract numbers from our system. And they're all going to work together. And now it's the same idea where we're going to need 7 logic gates, and they're going to be hooked up the exact same way that the other logic gates are. So the other logic gates, when the station turns on, it closes, and when it turns off, it opens. And I'm going to do the exact same thing. So at any time, these logic gates are, all the logic gates, if the third logic gate is open, the one on this side is also going to be open. They're always going to look or be in the exact same state as the other one that is opposite them. And that's so that both of these logic circuits are on the same track. They both know what the count currently is. Okay, so now I've hooked up these logic gates so they open and close in the exact same pattern as these logic gates that we have on the addition side of our circuit. So they will always be synchronized. They'll always look the same in their state of open and closed. Now to subtract, we have to do this a little differently. And I'm also going to put a protection circuit on this side as well. And for that, I need another counter and another logic gate. For this side of the circuit, it's a little different because by default, these are all off. And as I was explaining to you the way the addition works, if you hit 127 and hit another input, they're all going to turn off. If you're at 0 and you subtract 1, they're all going to turn on. It's kind of the exact same catch-all in there. And so you would go from 0 to 127. So we want to make sure that if you're at 0, you can't subtract anymore. And we're going to do it kind of in the same way. We're going to have this logic gate protecting us, and we're going to have this counter set to a count of 1. And we don't want to see this display. So what's going to happen is by default, logic gates are open, so I don't want this gate to do anything by default. So I'm going to be using the input blocked, which is what comes out if the gate is closed, as the input to this subtraction circuit. And I'm going to put a little button over there as well for my subtracting. And what I'm going to do is I'm going to attach the output of this to this counter. And I'm going to take the input blocked to decrease this counter. So when I'm adding, this counter will be adding, and when I'm subtracting, I'll be subtracting from this counter. So that once it hits 0 again, it will, 0 reached, it will make sure that this logic gate is open. And I set my target to 1. So when I reach my target of 1, I'm allowed to subtract again. So I will now close that logic gate. So I can now subtract, but if I hit 0, it'll reopen this logic gate so I can't subtract anymore. And that's really all we have to do. I'm also going to add another protection circuit here with another counter and another logic gate. Because if you recall my last tutorial, I was actually adding by 8 for a bit. Oh, and there's one thing else I forgot to do. I forgot to say if an input block comes out of this logic gate, and that's what is feeding our subtraction circuit, I want our visible counter to be able to know that. So I'm also going to decrement it by 1. And what I'm going to do here is I'm going to attach this button again to the input of this logic gate, and the output of this logic gate is going to be going to the logic gate that is going to increment my count by 8. And when I do that, I want all my counters to know that I've gone up by 8. Output will increment by 8 this one, which means my input block of my subtraction circuit also has to be able to tell this counter to decrement by 1. They all are going to be at the same count. Now, a nice thing I've found with counters, I don't want to show the display, is that the target reached, even if you use a number that skips over the actual number of your target count, say I'm going to set this target count to 120 because that is the highest divisible number of 8 that I can go before I pass 127. So I'm going to set it to 120, but let's say because I've added some 1s or subtract some numbers, I'm at 115 and then I add 8 to get to 123. This target reach will still fire if I pass that 120. And so what we're going to do is we're going to say if the target is reached, if we've gone over the number 120 or hit the number 120, I don't want to be able to add 8 anymore. The circuit up here will still work if I'm not at 127 yet, but I won't be able to add 8 anymore. So there we go. First, we're going to test our subtraction circuit a little bit. So if you see here, the binary is going along nice. We hit 4, we hit 5, 6, 7, 8. It's working very well so far. Now I haven't actually hooked up the subtraction circuit yet, and I'm now going to hook that up and show you how this is going to work. And how it's going to work is we're at the number 8 right now because this green light is on. And so how you subtract in binary is you go to a block, or you go to the least significant bit, and you start there, and you basically say, if it's 0, you change it to a 1, and you go, well, let's start on the simpler part. If this one was turned on, it would signify we're at the number 1. So any block that's on, if it's turned on, you just turn it off, and you're done. But if the first block is off, you have to turn it on and then move to the next block. If it's off, like this one is, you turn it on and move to the next block. And you keep carrying down the chain until you hit the first block that is on, and you turn it off. So in this case, what would happen is this one would turn on, this one would turn on, this one would turn on, this one would turn off, and we're done. And these 3 bits would represent the number 7, as I was just showing you when we went up in count. So it did, a circuit like that will actually subtract and give us a proper number. So what we're going to do is we're going to say, when we receive an input, if it's off, we want to send a signal to the next one. And we'll do that the whole way down. But if it's off, we also want it to turn on. So we will say, output, turn on, station 1. And we're going to do that the whole way down as well. And then we also want to say, if the logic gate is closed, or if that bit is set to 1, That is the one that we are going to turn off, and then we stop. So all we have to do is hook up our input block to turn off that station. And we do that the whole way down. So what we've done is, if it's on, we turn it off, and that's it. We stop. If it's off, we turn it on, and we go to the next gate to check if it's on or off. And we keep going down until we find a gate that's on, and we turn it off, and we stop. And that's all we do for the subtraction circuit. So now if I hit this button, we should find that this block, which represents the value 8, will turn off, and then 4, 2, and 1 will turn on, and 4 plus 2 plus 1 is 7. So we will subtract 1. And there we go, 7. And if we hit it again, because this one is on, all it will do is turn off, so that we will have 4 and 2 on, which will be 6. And now, what will happen is, because this one's off, it'll turn on, and it'll move on to this one, and it's on, so it will turn off. That way 4 and 1 will be on, which represents the count of 5. So there we have our circuit is working properly. We're going to move up to a big number and then subtract a few as well. Now I'm going to demonstrate here. Remember how we set a cutoff circuit on our 8 so that if we go above the number 120, our 8 will no longer work. So here we are at 125, and I'm going to push this button again, and nothing's going to happen. The cutoff circuit went into effect. We cannot go past it with the 8, but I can with the 1 still, because it hasn't reached 127. Now I'm going to subtract a few numbers, and we're going to go through the gate and see how it looks. 123. As we can see here, bits 7, 6, 5, and 4 are on, 3 is off, and 2 and 1 is on. That's a pretty good test to go through the gate and see if it can adequately see almost every bit is on except 1, and we're at the count 123. So we're just going to pop through this gate, and it shouldn't take long to load, so I'm just going to talk over the load just so you don't think I'm trying to cut anything out on you here. We are looking for the count to hit 123 when we got here, and we did it using our subtract circuit and our addition circuit, and there we go, 123, and it's a really fast and pretty good count system. So there we are. We used added a subtraction circuit to our 7-bit memory counter, and we just successfully moved the number 123 from one toy box to the next. This is Cimmerian again. I hope this has been helpful, and I will be back with another tutorial soon.